Look at your thumbnail right now. Go on, actually do it. Tilt it toward the light until you can see the surface texture, not the color, the topography. If you're under 25, you'll probably see a smooth, almost polished little plate. Past 40, though, you'll very likely see something else, a series of fine parallel ridges running from the cuticle all the way to the tip, like a plowed field seen from above. Almost nobody notices when these ridges show up. They don't hurt. They don't itch. They just appear, one birthday at a time, and by the time most people finally get around to asking a dermatologist about them, the answer is usually a shrug and the phrase normal aging. But normal isn't the same thing as unexplained. What's actually happening under that ridged surface is a precise, measurable record of 3 separate biological systems slowing down together. And one of the most rigorous datasets we have on the subject comes from a man who spent 35 years measuring a single fingernail on his own hand. Let's start with what a fingernail actually is, because most people have never really thought about this. The nail plate isn't skin. It's a slab of compacted dead cells, hardened keratin, manufactured continuously by a little factory of living tissue tucked underneath the base of your nail, hidden just beneath the cuticle. It's called the nail matrix. In a young adult, that matrix is a dense sheet of actively dividing keratinocytes, and it produces new plate material at a rate that's not just fast, but strikingly uniform. Uniform is really the key word here. Every region of the matrix, across its full width, is churning out keratin at almost exactly the same speed, which means the nail plate that comes out the other end is flat, because it was built off a perfectly even production line. Ridges show up when that production line stops being even. As the nail matrix ages, its keratinocyte turnover rate doesn't decline uniformly across the whole structure. It declines unevenly, in patches. Some columns of matrix cells are still cranking out keratin at close to the youthful rate, while the columns right next to them have already slowed way down. Picture a factory floor where some machines are still running full speed and the machines beside them are limping along at half. What comes off that line, physically, is a corrugated sheet. Peaks where production stayed high, valleys where it fell behind. That's the direct mechanical origin of what dermatologists call onychorrhexis, the longitudinal ridging pattern that becomes almost universal by the time you hit your 70s. You are, quite literally, looking at a growth rate map of your own matrix cells, printed in keratin, and the nail plate itself isn't even a single sheet. It's built from 3 distinct layers stacked on top of one another. A thin dorsal layer contributed by the uppermost matrix, a thick intermediate layer that makes up the bulk of the plate, and a very thin ventral layer added underneath by the nail bed as the plate travels forward. Each of these layers comes from a slightly different population of cells, with a slightly different sensitivity to slowing blood flow, and each one hardens at a slightly different rate. When you're young, all 3 layers get laid down so close together in time that the finished plate reads as one continuous glassy surface. But as matrix perfusion gets patchier with age, the layers start to drift very slightly out of sync with each other. The dorsal layer keratinizing a fraction of a day ahead of the intermediate layer sitting right beneath it. That tiny lag, compounded over the roughly 6 months it takes a full nail to grow from cuticle to tip, is enough on its own to create a fine, persistent corrugation, independent of any single cause. A ridge, in other words, is rarely the fingerprint of one broken system. It's what happens when several nearly synchronized production lines drift apart by fractions of a day, over and over, for months. But there's a second mechanism working underneath that one, and it actually explains why the unevenness starts in the first place. The nail matrix doesn't just float there. It sits directly on top of a bed of connective tissue laced with capillaries, and the interface between that vascular bed and the matrix above it isn't flat. In youth, it's folded, corrugated with microscopic little projections called dermal papillae, and those folds dramatically increase the surface area of contact between the blood supply and the keratin-producing tissue above it. More surface area means more efficient delivery of oxygen and nutrients to every single keratinocyte, which is exactly why young matrix tissue can sustain such a fast, even production rate in the first place. This folded architecture, by the way, is structurally identical to the rete ridge pattern that anchors your epidermis to your dermis pretty much everywhere else on your body. The same interdigitated, wave-like boundary that keeps skin resilient and well-fed, and it flattens with age. This is one of the most consistently documented findings in cutaneous aging research. The amplitude of that dermal-epidermal interdigitation measurably decreases decade over decade, driven by declining fibroblast activity, fewer collagen 7 anchoring fibrils, and a drop in the growth factors that maintain that folded geometry in the first place. When the folds flatten out, the surface area of vascular contact shrinks with them. Less surface area means less oxygen and glucose delivered per unit of matrix tissue, and the matrix compensates the only way it really can, by slowing keratin production and slowing it unevenly. Because blood flow doesn't decline identically across every square millimeter of tissue. Some patches of matrix happen to sit a little closer to a surviving capillary loop and keep producing just fine. Others sit a little farther away and fall behind. The ridge on your nail, then, is the printed record of a capillary bed losing its folds one column of cells at a time. Now here's the historical anchor, and it's a genuinely remarkable one. Back in 1938, a young physician named William Bean started measuring the growth rate of his own left thumbnail. He'd mark a small notch near the cuticle and track, with a ruler, exactly how far it traveled each week. And he kept measuring it, the same nail, the same method, for the next 35 years, publishing his results periodically in the Archives of Internal Medicine and later in the Journal of Gerontology. What he found, tracked across his own aging body from his 20s into his 60s, was a growth rate that fell from roughly 0.123 millimeters per day as a young man to roughly 0.095 millimeters per day by the time he reached his 60s, a decline of nearly a quarter, unfolding gradually and almost linearly across 4 decades. Bean's data is, to this day, one of the longest continuous self-experiments in the history of physiology, and it turns the abstract idea of a slowing keratin factory into an exact personal number. Your nail is quite literally growing slower than it did when you were young, and it's doing so on a predictable biological schedule. And here's where the two mechanisms actually converge into something worth sitting with for a second. A slower matrix isn't simply a matrix producing less keratin per day. It's a matrix that has more time between one keratinocyte's birth and its final compaction into hardened plate for small irregularities in that production to become locked into permanent structure. Fast-growing young nail plate essentially outruns its own imperfections. Little pockets of slightly slower or slightly faster keratinization get compressed and smoothed out before they can ever become visible topography. Slow-growing older nail plate doesn't get that luxury. Every small variation in the underlying vascular supply gets faithfully translated, at low speed, into a ridge you can feel with your fingertip. The ridging isn't a separate process from the slowdown Bean measured. It's what a slowdown looks like when it happens unevenly, across a folding capillary bed that is itself losing its folds. Now, the evidence calibration, because this is a point where the science is stronger in some places than others. The relationship between chronological aging and increased longitudinal ridging is extremely well replicated across the dermatology literature. That part isn't controversial at all. Mechanistic chain connecting flattened dermal papillae to reduced matrix perfusion to uneven keratinocyte turnover is anatomically well supported and lines up with everything we know about skin. Aging elsewhere on the body, but the nail-specific vascular studies are fewer in number than the broader skin studies. So some of that connective tissue is inferenced by strong analogy rather than direct nail matrix microscopy. What's not well supported is the popular claim that ridges themselves point to some specific vitamin deficiency or dehydration. Sudden deep horizontal grooves called Beau's lines can genuinely signal acute illness or nutritional shock. That part's real. But the fine, gradual, vertical ridging that builds up with ordinary aging is a completely different phenomenon, and no rigorous study has ever shown that supplementation reverses it. This is aging tissue architecture. It's not a deficiency you can fix with a pill. There's a bigger implication worth naming directly here. Every visible surface of your body that depends on a matrix of dividing cells sitting on top of a vascular bed, your skin, your hair follicles, the nail matrix, seems to be running the exact same aging program underneath. The folded interface between tissue and blood supply flattens out, delivery efficiency drops, and production gets slower and less uniform. Your nails just happen to be the one place where that entire process gets recorded permanently, in a hard material, in a straight line you can run your thumb across. Wrinkles fade in and out with hydration and expression. Hair thins gradually and diffusely, all over, hard to pin down. But a nail ridge, once it's grown out past the matrix, is fixed. It's an unchangeable printout of exactly how evenly your capillary bed was feeding your cells during the specific weeks that section of nail was being formed. So go back to your thumbnail one more time. That texture you felt at the very start isn't damage, and it isn't decline in any simple sense. It's a physical transcript, 3 to 6 months old, depending on how far up the plate you're looking, of a capillary bed folding itself flatter, and a cellular factory falling slightly, unevenly, out of sync with itself. William Bean spent 35 years proving that this slowdown is real, gradual, and measurable in millimeters per day. You're carrying the same proof on the end of your own finger. You always have been,